All right, what follows here is a handy-dandy 9-step plan to get Lewis structures. Now, the whole idea with this procedure that I like to use is that electrons aren't necessarily assigned to a particular atom or not. It's kind of like, for carbon dioxide, which is going to be our first example, what's the best way to arrange a carbon atom, 2 oxygen atoms, and whatever number of valence electrons we've got around there to not make them fly apart. Now, I will say that I will put on Learn a handout with this procedure, and I've also have a copy of the group activity that we would have done had we been doing this in person, that also has the steps kind of blocked out like this, and it's got a few more examples in there. So you might want to maybe bring that up, print it out, and follow along as we're going through this example. So the first step is to separate cations and anions if what you're working on is an ionic compound. There is no sharing of electrons between the ions in an ionic compound, so the sharing doesn't apply. Now, keep in mind that ionic species can be covalently bound. The polyatomic ions, like ammonium and sulfate, are actually internally covalently bound. But in this case, we don't need to worry about this. So let's put a big ol' Na here. Now, the next thing is to add up all the valence electrons, and this is actually kind of important. So we know that there are 4 coming in from the carbon, and the oxygens are contributing 6 apiece. And that gives us 4 plus 12, 16 valence electrons. All right, so the next thing is to assemble the bonding framework. And what do we mean by that? The way that this is written, bring up here now, this is sort of like a y to the z. Whenever you see a molecule written like this, the first element, usually of which there's only 1 atom, that's going to be in the middle. And so this is telling you that, unless otherwise told, this is a carbon. And for the framework, you just want 1 single bond connecting everything together, because if it's part of a molecule, there's going to be at least one bond there. So this is the bonding framework for carbon dioxide. And in making these 2 single bonds, we have used 2 pair or 4 of the 16 electrons. All right, so let me redraw my bonding framework here. So we've got carbon and the oxygen. So we had 16 electrons. We used up 4 of them there. And the next step is to put 3 unshared electron pairs around all the peripheral atoms, unless it's hydrogen. Hydrogen only can form a single bond, and that's it. So I'm just going to start putting unshared pairs around the oxygen atoms. So I've got 4 electrons already. That's 5. That's 6. That's 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And that's all of them. Now, the next step, if you were to have electrons left over at this point, then they go as unshared pairs on the central atom. But in this case, we don't need to do that. So now the next thing is to check for formal charge and octet issues. So let's talk about this here. So let's go back up to the structure. And so by formal charge, by octet counting, let's look at that first. That the oxygen actually has an octet. So it's got these 6 unshared electrons and the shared pair bringing it up to 8. Same for this oxygen. But there's a problem with this carbon. That it only has, by formal charge counting, 1 electron from this pair, 1 electron from this pair, which is 2. Or let me rephrase that. From an octet standpoint, it's only got 4 electrons and not the 8 that it wants. So this is short its octet. Now I'm going to go back here. So that's a problem. And the other thing to look at, I'm going to draw this. Oops. Switch to the pen here. I'm going to draw this again. All right, so let's look at what the formal charges are. I'm going to switch the color here. Let's do purple. So let's look at the formal charge on the carbon atom, or the oxygen atom here. Oxygen usually has 6 valence electrons. Now in this structure, it has 1, 2, 3, 4, 5, 6, 7 electrons associated with it, which means that this has a formal charge of -1. And this oxygen atom is the same. Now, let me ask you to figure out what the formal charge on the carbon is. Hit pause, think about it. Now, the carbon atom here usually has 4 electrons. By formal charge counting, this only has 2. I mean, half of this pair, half of that pair, which means that that has a formal charge of +2. And formal charge is bad. You want to get rid of it. And the way that we get rid of formal charge and the way that we fix this octet problem is actually the same thing. And we simply move one of the unshared pairs from the outside atoms to being a shared pair here. Don't forget to cross that out. So now let's look at what this has done to the formal charge. Now, let's look at the octet issue. Has the octet issue changed for that oxygen? No, it hasn't. It's still got the 2 unshared electron pairs. It's got the 2 bonding pairs. So that still has an octet. But now the carbon has gotten closer to it. Because now by octet counting, this now has 6 electrons where it had 4 before. And is the formal charge better? Well, let's look at the formal charge now. So in this structure, it now has, again, usually has 6 electrons associated with it. But in this structure, it now has 1, 2, 3, 4, 5, 6 associated with it, equals 0. So this formal charge has improved from -1 to 0, and that's as good as it gets. Now, what about the carbon atom here? This carbon atom, again, usually has 4 valence electrons. In this structure, it has 1, 2, 3 assigned to it. So its formal charge has now gone down from +1 to +2. That's also an improvement. And you go through this process and nothing's happened to other oxygen. And basically you keep going through this process, which is the next step.